second plenary lecture. So the schedule is very tight, so we'll start right ahead. The first talk was about curves and surfaces, so dimension 1 and 2. The next talk is about dimension 3 and 4. So, it's my great pleasure to introduce Professor Jae Choon from Postech, Pohang University of Science and Technology. So let me briefly introduce his professional career. So he had his PhD at KAIST at 2000, as well as his master's and bachelor's degree at KAIST. And he had several positions, assistant professor positions at KAIST and ICU. And from 2007, he has been working at Postech. And he received many awards. One of them is the Scientist of the Month from Ministry of Education and Science at 2011. And also he received Korean Math Society Research Paper Award at 2009. So let's welcome Professor Jae Choon.
Thank you very much. This is my great honor to have this opportunity to deliver a talk in this wonderful joint meeting of KMS and DMV. Thank you very much for the organizers of this event. So today, I'm going to talk about some sort of Hilbert type invariance and its relationship and recent advances using it in the topology of dimension 3 and 4. So, all right, so let's begin with Hilbert. Last night, I was pretty busy with something. I mean, preparing this talk, and I thought it could be nice to put a photo of Hilbert here. So I Googled, and I found a really good picture shown here, interestingly from New York Times. So, okay, and I really liked that because it was his last lecture given at Max Planck Institute for Mathematics in Bonn, where I spent my last sabbatical. So I really liked it, but I thought, wait a minute, what about copyright issue? New York Times could be very strict about their own copyright, so I was a little bit worried because today I'm just employee, and they might sue KMS and DMV instead of me, and I don't want to have that kind of troubles. So I Googled a little bit more, and unexpectedly I found that this was actually taken by a mathematician. And indeed, it was my close friend, German friend, the mathematician Stefan Friedl at Regensburg. So I was so pleased without having any potential copyright issues. So this is his picture. All right, so he defined a signature defect invariant. I will explain it in a minute. In 1967, which was before I was born, for closed manifolds of dimension 4k-1 with pi 1 cyclic of order 2. So let's begin with something very elementary. I always believe starting with elementary things is nice. So here is a symmetric square matrix with real entries or equivalently symmetric bilinear pairing defined on a finite dimensional vector space. Then the signature of this pairing or matrix is defined by taking the difference of the number of positive eigenvalues counted with multiplicity and number of negative eigenvalues. Okay, so this is an integer. Or we could take the subspace on which the positive definite part of this bilinear pairing and negative definite part, v plus and v minus here, and the zero part. And then we just take the dimension of the positive definite part, dimension of the negative definite part, and take the difference. That's the signature. Okay, this is an elementary invariant of bilinear pairing. So in topology, using this, we define the signature of a manifold when its dimension is 4K. So here is a manifold which is compact. Whenever I say manifold, it's compact today and oriented. Then Poincaré duality gives us the intersection form in the middle dimensional homology. Geometrically, this is none more than counting the signed intersection numbers between 2K middle dimensional, let's say for instance submanifolds, and then that gives us an integer. Let's just use real coefficients. Then this is a bilinear pairing, so we can take its signature. So this is defined to be the signature of the 4K manifold W here. Okay. So Hirzebruch now considered a closed 4K minus 1 dimensional manifold. So for this thing, we don't define, the signature is not directly defined, but he did the following. So suppose that its pi 1 is cyclic group of order 2, and then Boldism theory tells us that there is a 4K dimensional manifold bounded by some copies, disjoint union of some copies of the given M. And this bounding is over the group G mod 2. That means, okay, picture is always easier to see, I guess. So I have those disjoint union of disjoint copies of M here, and W is bounded by this union. And then we have that, okay, here, this is just the pi 1 of those boundary components, and we have this map, the identity on each component, and then the requirement is that this map factors through this bounding 4K manifold. We always have this situation by Boldism theory, and then he defined an invariant by taking the signature of the associated double cover of the 4K manifold. Because we have this map, there is an associated twofold cover whose transformation group is G mod 2, and then take the 2 times of the signature of the W. So this is, we have 2 here because this is double cover, so it's making the this term and this term fair. So, and then we divide it by the number of multiple copies used here. This is his invariant. So this is interestingly well defined, independent of the choice of this 4K manifold. So this is an invariant of M. He used this to understand the involution, namely free actions, fixed point free actions of G2 on manifolds. And starting from his initial introduction, this was generalized by several people. So I could mention, first of all, Wall's work. In his study of surgery, he generalized Hirzebruch's invariant for the case of finite fundamental group. This generalization is very straightforward. Indeed, we can just replace this number 2, which appeared because we used double cover, by the order of this finite fundamental group. So that's along the same lines. And Attia, Patodi, and Singer, they generalized the idea of Hirzebruch to the case of arbitrary pi 1, but still this is essentially about finite dimensional case because they used finite dimensional unitary representations of the fundamental group to play a similar game. More interesting thing about Attia, Patodi, Singer is that they obtained the invariant of the given M, 4K minus 1 dimensional manifold, without using bounding manifold W. That's the real new thing of Attia, Patodi, Singer. They actually used instead a Riemannian metric on the given manifold M and used their index theory to consider spectral eta invariance of the signature operator to obtain a generalization of Hirzebruch's invariant. So this became purely about M without using extra W. And Chigger and Gromov generalized this, Attia, Patodi, Singer, to the case of actual infinite dimensional situation. So they generalized at the part of the single to the infinite dimensional case by using some operator algebra. In particular, they used the von Neumann trace of operator algebra to define a sort of L2 type eta invariant of at the part of the single. So this is done without using W on the nose at least. But now I'm going to tell you how to interpret the invariant of Chigo and Gromov using the original idea of Hilsbrook. So here is a 4K minus 1 dimensional manifold M, and here is an arbitrary group homomorphism of the fundamental group. And the really nice and useful observation of Schimmel-Weinberger is that there is a monomorphism of this group, target group gamma, into another group G. And if we replace gamma by G, then now we can find a bounding 4K manifold whose boundary is certain disjoint union of the given M now over this new group G. So we have a similar diagram, but now we use a supergroup G. And then the whole point of this idea is that if we play with L2 invariants, then replacing a group by a bigger group, namely composing with an injection, doesn't change the invariant. So it turns out that we can use this W, which is now over the new group G. And here the problem is that because we started with an arbitrary group homomorphism, now the covering space we want to use is not necessarily compact, and therefore the homology is not necessarily finite dimensional, so we can't define the signature directly. So here we use the L2 signature. So they take the L2 signature of W and take the usual signature and take the difference similarly to the previous finite dimensional case to define their Chigo-Gromov row invariant. So what is the L2 signature? Let me just describe it briefly. Okay, so the usual real coefficient homology of the covering space is equal to the homology of the original space with coefficients in a group ring of the given transformation group. This is standard fact from elementary algebraic topology. And the idea of the L2 invariant is to use, instead of the group ring, we use the group von Neumann algebra. So we employ some analysis. So we think of the Hilbert space completion of the complex coefficient group ring, and then think of the operator algebra of bounded linear operators on this Hilbert space, and we take the completion of the group ring inside this operator algebra. That's the group von Neumann algebra denoted by here NG, and then given a 4 manifold and this group homomorphism, 4K manifold and a group homomorphism. As before, we use the Poincare duality to obtain the intersection form, but now this intersection form is twisted, namely it's now over the von Neumann algebra NG, and then we use another thing from analysis. Spectral theory on operator algebra enables us to obtain the similar decomposition of consisting of the positive definite part, V plus, and negative definite part, V minus, and zero part. And then now we can consider so-called L2 dimension, which is defined for any modules over the group von Neumann algebra. This is defined using the von Neumann trace on the operator algebra, so that we can define the signature in a similar way. So this is the L2 generalization of the Hilsbrook signature defect, which is much more general. Okay, the goal of today is to talk about some geometric applications in low-dimensional topology. And often, low-dimensional topology is defined to be the study of dimension 4 and 3, and sometimes 2 and 1 as well. Yeah, so part 2 of my talk is devoted to dimension 4. Okay, so in high dimensions, it's well known that we have the ultimate machinery of surgery theory. It works in high dimensions so that manifolds can be understood via the algebraic problems about surgery obstructions, namely L groups, and homotopy theory of associated bundles, smooth bundles or topological bundles. So this is really wonderful. So what makes this possible, particularly for surgery theory, is the well-known technique of Whitney, which can be used to remove intersections of submanifolds. Very roughly speaking, in order to carry out surgery, we need to cut the given manifold along certain submanifold, usually just an embedded sphere. It's important to have something embedded. If it's immersed, then near intersections, it's really difficult to control what happens. Like the actual surgeons do, they always cut our body in a straight line. We are a little bit more sophisticated in doing topology. We cut along spheres, but it should be embedded. Okay? So we want to remove intersections between the self-intersections or mutual intersections of spheres, or more generally submanifolds. So the Whitney move removes, let's say, for instance, those two intersections between two sheets denoted by A and B. To do that, we use a disk, two-dimensional disk, bounded by this arc joining those two intersections in sheet A and this arc in sheet B. Once we have this, we can do a very easy geometric operation, just to push one sheet along the red disk in this picture. Then we get something like this. Right? Intuitively, it's very easy to see that those two intersections are now removed. So this is the core technique used in surgery. So to do this, we need this embedded disk, D, which is now always two-dimensional because it's bounded by this one-dimensional circle. So making a two-dimensional disk embedded is very easy if the dimension is at least 5, because 2 plus 2 is smaller than 5. That's easy arithmetic. But in dimension 4, it's a disaster. It's extremely difficult to remove self-intersections of two-dimensional disks. And this is why dimension 4 is still left mysterious. I would say dimension 4 is the least understood dimension for us because of this difficulty. So disk embedding is extremely important to study dimension 4, and we often interested in topological case and smooth case. The big discovery was due to Friedman and Donaldson in the 80s. Friedman proved really amazing disk embedding theorem, which can be used for the situation of simply connected surgery problem for four manifolds. And using this, he proved the Poincaré conjecture, topological version in dimension 4, and he classified simply connected four manifolds, and a lot more applications was found. On the other hand, Donaldson, proved his famous diagonalization theorem for simply connected smooth now four manifolds with definite intersection form, and this indirectly tells us that disk embedding fails in the smooth case even when the precise analogs are true in the topological case. So we have the difference between the categories. So let me first discuss the topological category and then come back to the smooth category. Okay, so let me describe the general disk embedding problem in dimension 4. Okay, I always prefer pictures, so it's not very precise, but I hope this is easier to see. I have a four manifold now, W, and here is the boundary W, and I have a link. A link is none more than a disjoint union of finitely many circles embedded. Okay? So I have two circles here embedded in the boundary. So this is a three-manifold, one-dimensional object in three-manifold. And then the problem is to determine whether there are disjointly embedded two-dimensional disks in this four-manifold bounded by this given link. So do we have such a thing? Right? Disjointly embedded. So that's a formulation of general case of this disk embedding problem. And a very important particular case is the local case, namely when W is D4, the standard 4 space, so that, for instance, there is no difficulties and obstructions from homotopy theory, then its boundary is the standard 3 space, S3, the same as the actual physical world we live in. And my link is now something in our space, okay? So can we find such embedded disks for this case? That's the local problem, okay? If there is a solution, namely if L is the boundary of embedded disks, disjoint embedded disks in D4, then we say that L is a slice link, because it's a slice of two-dimensional disks. And often we ask the question in the topological category and smooth category. Both are interesting. And it's known that similarly to the typical local global principles in, for instance, in number theory and algebra, it's known that if we have had a complete solution to this local case link slicing problem, then we would be able to get an answer to the general topological surgery problem. The topological surgery problem in dimension 4 asks whether topological surgery machinery works for arbitrary fundamental group. Friedman's wonderful discovery was that this can be done in the case of simply connected four manifolds, and more generally when the pi 1 is not too complicated, very briefly speaking. But the central question here is whether topological surgery works for any case. And this local case is the complete understanding of the local case will give us an answer. So let me show you some examples. Here is a link. How many components do we have? I see one component, second, and third. So this is a 3-component link, which is called the Borromean rings. Okay, so if you, just for fun, if you get rid of one of these 3 components, then you will see easily that the remaining 2 components are completely separated. Okay, so this is such a link. This link, is it sliced or not? We may ask that question, but we know the answer, so this is not the real problem. This was answered much earlier than actually by John Milner in his bachelor's thesis indeed. So this is too easy. So the actual question is about this guy. Okay, so we doubled each component in a certain way. So originally, for instance, I had this component, but this has been now doubled here. So this is called the whited double of Borromean rings. Okay, is this sliced or not? We don't know. Another example, whited double of a certain guy called ramified whited link. So this also has 3 components. Is this sliced or not? We don't know. Why are we interested in this? Because if one of them is not sliced, then an immediate consequence is that topological surgery fails. So can we show that this is not sliced? So in order to understand the disk embedding problem, we attack from 2 sides. Can you embed? Can you find a solution? Or do we have an obstruction? So here is an extreme case for which there are solutions. And here is the other extreme case for which we don't have. We do know that there are no solutions. And try to enlarge those 2 clashes. And if we arrive at a common bother, then we are done. So, but fortunately, fortunately actually for me, because my career is still pretty much, I need to prove more things. It's not yet at that stage. So we have big gap between those 2 classes. So let me tell you a little bit about the results of known results. First about the existence results. So Friedman showed the disk embedding for Casson towers of height 6. A Casson tower is a kind of 2-dimensional complex which approximates, roughly speaking, desired embedded disks. And this was actually enough to prove his results about topological surgery and Poincare conjecture. And let me just mention that this link is indeed almost equivalent to thinking about Casson towers of height 3. So if we could do height 3, then we would be done. But what Friedman did was only for height 6, but this is already enough to prove the Poincare conjecture in dimension 4. And later, Friedman and Friedman-Teichner, they proved more slicing results for certain white-headed doubles. And more recently, myself, together with Mark Powell, proved disk embedding theorems for Casson towers of height 4. So this is pretty good, but it's not yet to the final goal. So we have something to do here. On the other hand, let me focus on now non-existence results, namely obstructions to disk embedding. The game was started, I would say, by Jerome Levin in the 60s. Actually, he developed a high-dimensional theory, but it gave us invariants and obstructions for disk embedding in dimension 4. And Casson and Gordon actually used the Hilsbrook-type signature defect invariants over the product of infinite cyclic group and Gmod PA, where P is a prime. And the game changer was the work of Cochrane-Teichner. They used the Chicago for L2 signature defect, L2 row invariant, over certain special types of groups to obtain a lot more stronger obstruction than Casson and Gordon. And this was the start of a lot of new applications in related problems in dimension 4. And for now, the strongest known result is the following thing, which is called the amenable signature theorem. This is partly joined with Kent Orr at Indiana University. So suppose I have a knot which is a topologically sliced. It bounds a topological slicing disk in D4. And then let's think of this 4-manifold W obtained by removing a tubular neighborhood. So this is my knot. This red is slicing disk. And I thicken this slicing disk a little bit, as shown here, and then get rid of this thing. Then that's a new manifold W whose boundary is so-called the zero surgery manifold of the knot. So this boundary is something fixed, but this 4-manifold depends on the slicing disk. And suppose that I have a homomorphism of the pi 1 of this 3-manifold, which extends to this 4-manifold. And, very important, suppose that the group G here is amenable and locally p-indicable. Then the Hilsbrook type L2 signature defect, namely Chicago-Gromf row invariant, is 0. So this vanishing is an obstruction. If this is non-zero, then we can conclude that there's no slicing disk. Okay, so this is the same theorem with some part omitted here. So I didn't tell you about the conditions assumed about the group. So let me just try to tell you something very brief. A group is locally p-indicable if every non-trivial subgroup surjects onto Gmod P, cyclic group of order P, where P is a prime. This is an algebraic condition. And G is amenable if there is a finitely additive invariant probability measure on the group. Invariant means it's invariant under the action of the group elements. So these two conditions are extremely important. So let me just remind you the original motivation of the amenability. Banach-Tarski paradox, which is very well known. So if the dimension is at least 3, then in the Euclidean space, let's just take a little cube. And then it's possible, the paradox tells us that it's possible to decompose this into finitely many disjoint pieces, and we can reassemble them by using some Euclidean isometries to get an arbitrary size cube. The volume can be doubled, for instance. So it's called a paradox, even though this is a theorem, because it's very unlikely. So the amenability is actually very closely related to this. Von Neumann and Tarski, they showed that Banach-Tarski happens if and only if the associated isometric group of this space is not amenable. So it means that, in other words, it's amenable if it's not wild. It's kind of tameness. So we wonder whether this kind of original motivation of amenability is related to disk embedding. It was a long-standing question, and the amenable signature theorem here is a first theorem which actually relates amenability to disk embedding. But its actual proof is very far from this original idea. In the proof, we just use a sort of more or less algebraic analysis fact that the von Neumann group algebra, group von Neumann group algebra is flat to the ice of L2 dimensions, namely the L2 dimension of Tor functor. When ng is involved like this, is always 0 in high dimensions. This is a result of Wolfgang Loch in 2002. So we use the amenability in a very indirect way. So that's still a very interesting question, whether this original motivation is related to disk embedding. Okay, so among applications, many people studied the knot concordance group. This is the set of equivalence classes of knots modulo slice knots, where the group operation is given by connected sum. What is connected sum? Here is a knot, another knot, just to connect them, okay? Picture is much easier to understand. So this is the group operation. It becomes a group under this, and understanding the structure of this abelian group is a major problem. So in particular, Cochran, Harvey, and Leidy, in a series of their papers, they used the Chigo-Gromf row invariant, or equivalently Hilbert type L2 signature defects to reveal very interesting structures in this group. And there are other related subjects for which we made people made the applications of Hilbert type L2 signature defects, like homology cobordism of three-manifold, homology cylinders, which in particular includes mapping class groups, and more recent idea of L2 acyclic Boltzmann group. But let me just more focus on the idea of groups and Whitney towers in dimension 4. What is a group? So here is a knot, and we wanted to find a disk, but what can you do if we don't find a disk? Then it's much easier to find a surface with higher genus. So this is a genus 1 surface, but this is not a disk. So we want to promote this guy into something which is closer to an embedded disk. So the attempt is to take a second stage. So take these basis curves and attach for second stage surfaces. So this is called a group of height 2 because we have 2 stages. We can proceed. This is a group of height 3. So a big question in this context is whether if A knot bounds an infinite height group. So I can't draw it, but you can easily imagine what an infinite height group is. If that happens, then is K slice, namely, is there an embedded disk bounded by the knot? That's a big problem. And the amenable signatures theorem I stated above is the only known potential obstruction to this problem, but it's still open. So this is something very interesting. All right, so let me just discuss very quickly about the difference between smooth and topological case and its relationship with Chigo-Gromf row invariant. So in the context of knot slicing, we often think of the following abelian group. Now we think of topologically sliced knots. So for this knot, we have solution to the disk embedding problem in the topological category. And we think of them modulo now smoothly sliced knots. The group operation is the same connected sum, and this group measures the difference between those 2 categories. So this is a very interesting problem to understand this group. And it was shown that this is non-trivial by Kessler and Arkwright immediately after the work of Friedman and Donaldson using their results. And we do know, for instance, that it's of infinite rank due to Endo. And there are many interesting results about this. And modern smooth technologies are often used to obtain obstructions to being smoothly sliced, namely to being trivial in this group. So they include gauge theory, both instanton and monopole, and Kovanov homology, Haggard flow homology of Ozbas and Jabo. Many recent technologies are very useful in this study. And Cochran, Harvey, and Horn recently introduced a really nice way to organize the structure in this group called bipolar filtration. So we are interested in this group T, and they defined a descending filtration consisting of nested subgroups, where these terms are defined, very briefly speaking, by combining ideas from the work of Donaldson, namely the idea of importance of definiteness in smooth form manifolds and the idea of Friedman about groups we just briefly discussed in the previous slide. And the really interesting fact is that modern smooth obstructions I just described above, from gauge theory and Haggard flow and other things, these smooth obstructions are all trivial if you go to the first stage or higher. So smooth obstructions does not detect the situations in the deeper part of this filtration. So the question is the following: is this filtration actually non-stable? Is it just zero from here? So this question was difficult to answer because of the lack of the technology. Smooth invariants are not useful in the deeper parts. So Cochran, Harvey, Horn showed that the first two associate grades are non-trivial, grades are non-trivial. So a recent result of myself with my former student, Min-Hoon Kim at KIAS, is that this filtration has non-trivial graded quotients at every stage. And this was interestingly proven by using amenable signature theorem together with Haggard flow homology. If we use Haggard flow only, then it's useless because it vanishes here. Amenable signature theorem is about topological thing, so it's obviously trivial here because everything here is considered here is topologically sliced. But combining them, we can actually extract new information about smooth case. So this is pretty interesting application of Hirzebruch type L2 signature defects. Okay, in the remaining time, I have about 10 minutes, I think. So I'm going to discuss dimension 3. That's the part 3 of my talk. Oh, it's pretty fun to have part 3 about dimension 3, but I can't have part 4 about dimension 4 because I already discussed part 4, but next time I will try to organize things in that way. Okay, so let's just go on. Dimension 3. So let me start with some motivation from dimension 4, although I will focus on dimension 3 in a minute. Unfortunately, even though this Chicago flow invariant is extremely useful, its computation is very difficult. It's almost impossible to determine the value of the Hirzebruch type L2 signature defect in general case. So we use often some kind of estimate for the study of dimension 4 given by in the original work of Chigo and Gromov. It says the following: for every smooth manifold 4k-1 dimensional, there is a constant Cm here such that the value of the row invariant, L2 row invariant, is bounded by this constant for any choice of homomorphism. This is a really strong thing because in general we have, when pi 1 is generic, we have infinitely many homomorphisms, so this is a bound for infinitely many values. And this was actually one of the main ingredients in the proof of Chigo-Gromov's L2 index theory. So, and later, Cochran and Teichner was the first people who discovered the usefulness of this estimate, the existence of such an estimate in the study of dimension 4. And then we had a lot of applications of this. But the proof, I'm a topologist, and unfortunately, the proof of Chigo and Gromov relies on very deep analytic techniques using a choice of Riemannian metric, which is pretty arbitrary, and it doesn't reflect many things of anything about topology. So it's deep. It means, honestly speaking, I don't understand their proof. So we topologists try to understand this better from a topological viewpoint. So the question asked by several people was to get some better topological understanding of this constant, and in particular, any explicit estimate. For example, this is a 3-manifold obtained by so-called dense surgery. This is one very simple case of a 3-manifold, but for this thing, because of due to Cheeger graph, we do know that there is a constant CM with this property, but how large is it? We have no idea. 10, 100, million, billion. We have no idea about the size of this constant beyond its existence. So the first result I want to introduce regarding this problem is that, okay, it states that for every now topological manifold, there is the constant. So this is the generalization to the topological case. To prove this, we can't use the technique of Cheeger and Grove, which was really analytic, using a Riemannian metric. So indeed, the proof is very topological, and I used Hilsbrook type L2 signature defect interpretation of the row invariant. So this is one very pretty satisfactory step. And if I think of three manifolds, then actually this new method, the idea of this proof, tells us a lot more than just the existence. So let's think of the following. Any three manifold has a triangulation, and then let's think of the number of tetrahedra. This is just the number of building blocks of your Lego idea. If you want to build a shape by Lego blocks, if you need more number of Lego blocks, then it means that your shape is more complicated. So this measure, this number CM defined here, minimum number of tetrahedra in a triangulation, measures how complicated your three-manifold M is. So this is often called the complexity of M. So the first theorem I want to tell you about this three-dimensional case is that for any group homomorphism of your three-manifold, pi 1 over your three-manifold, we have this inequality. Here is an explicit bound in terms of this complexity, given with this weird 9-digit number. So this is the largest number I actually used in my mathematical life. So, okay, let me try to tell you just very little bit about how and from where we obtain this large number. And here is one more thing. This upper bound is optimal. Oh, you wouldn't believe that because this constant is too large. So here is a secret about this space. It's asymptotically optimal. It just means that this is a linear upper bound and linear is the best. Okay? Okay, so this is the theorem I just stated. And this statement that it's asymptotically optimal says the following. We can think of, by taking just the supremum of all possible values for complexity n most to n, it gives us a function representing the smallest possible upper bound, and then we compare this best upper bound with the linear function, and then it says that this theorem says that the asymptotic growth is the same with the linear function. So we explicitly determine those constant bounds, non-zero constant bounds. So let me just discuss quickly about the idea of the proof, which I think interesting on its own. Recall that we defined the row invariant following the idea of Hilsbrook as a signature defect, L2 signature and usual signature. And here is a very convincing fact that those signatures are small if the four-manifold W is small. If manifold is small, then chain complex is small, and then homology is small, and so signature is small. That's the idea. For instance, if the number of two handles of my four-manifold W is small, then those signatures are bounded, and therefore this row invariant is bounded. That's from how we get this explicit bound. So natural question arising from this easy observation is how we can obtain a small bounding four-manifold. Okay, that's the question. And then here's an easier question. When does this exist? So measuring the size can be done after understanding the existence, but the existence is a classical question. It's just a Boldism theory. There is a desired four-manifold if and only if the given three-manifold is trivial in the Boldism group, and the Boldism group is computed from homology groups by Attia-Hilsbrook spectral sequence for Boldism, and it turns out that the it exists, solution exists, if and only if it's null homologous in third homology, namely the fundamental class of the three manifold bound some chain in the chain complex. So this is an algebraic analog. This chain U I wrote here is an algebraic analog of this geometric solution. So we need to understand those things quantitatively. So this introduces the need of quantitative study of topology. One day, in the meeting of Canadian Math Society, in a plenary talk, Samuel Weinberger told us that Jean-Pierre Serre ruined algebraic topology. It's pretty bold statement, but he meant that Serre gave us really wonderful technology like spectral sequences, but that gave us the really good information about the existence of a solution, but it's now really difficult to understand the nature, geometric nature of this solution. So we want to understand the geometric complexity of these solutions, so we want to understand the size of these solutions of this algebraic solution and geometric solution. So for this purpose, we developed, first of all, geometric version of Atiyah-Hirzebruch Boldism spectral sequence with some control. So instead of using algebraic approaches, we use now geometric approaches. And second, to resolve this, understand this algebraic analog, algebraic solution in full chain complex, we developed the theory of controlled chain homotopy. So this includes controlled acyclic model theorem, and for instance, controlled Eilenberg-Gilbert theorem. So these are all new things, and I think those are interesting on its own. So in the remaining 1 minute, this is a slide I want to skip. Let me just state and introduce a new application. So the complexity was defined before, but it's easy to define, but the computation is extremely difficult. An upper bound is easy to obtain. Any triangulation gives us a bound, upper bound, but finding an efficient lower bound is very difficult. So people try to extract some efficient bound, like from basic information like homology and hyperbolic volume, and more remarkably, Jacob, Rubinstein, Tillman used double covers and G2 version of Thurston norm, but even for very simple three manifolds, complexity is left unknown. For instance, the simplest case of lens spaces, just a quotient space of the standard free action of cyclic group of order n on standard 3 space, even for this lens space, we only have conjectures. The complexity is conjectured to be the same as n-3 for Ln1, but this was proven for even n by Jacob, Rubinstein, Tillman, but for odd n, almost nothing was known because of the lack of efficient lower bound. But recall that my theorem gave this inequality, and if I change the viewpoint, then this can be viewed as now a lower bound for this complexity. I know that this is very small because of this big denominator, but it turns out that this is very useful. Indeed, I showed that the complexity of those lens spaces is asymptotically linear in n. Namely, it's between the conjectured value and the conjectured value divided by this large number. So this confirms the conjecture asymptotically. So the remaining thing to prove this conjecture is now to improve this constant to 1. That's pretty non-trivial to do, I think. But perhaps myself or by more possibly by somebody else, that could be answered hopefully before the second joint meeting of KMS and DMV, hopefully. We don't know yet when it's going to be, but I hope. So let me finish here for today. Thank you very much.
So I'd like to thank Professor Cha for his very interesting talk. So any questions or remarks? I have one. Are there any questions? So I have one question. Do Do you think this surgery works for dimension 4 or not?
Yeah, that's a tough question. Let me just use some big names instead of my own opinion. Friedman and Teichner believe that it's not going to work. But it's the questions about how to prove. So actually, we barely know about that. That's very challenging. Yeah.
Thank you very much. Let's thank for the speaker again.
Thank you very much.